Welcome back everyone. In this lecture, let us talk about partition of a set in a more abstract way, and then we try to understand them using our cosets. Okay, let us start with a set capital X. Let's assume it to be a non-empty set. So, this is a non-empty set. So, a partition of this set capital X, it is a collection of subsets of capital X. Let us call them A alpha. Alpha runs over some indexing set capital lambda. Okay. So, this is called a partition of capital X if the following happens. So, first they are all subsets, A alphas are all subsets of X, and then they cover entire X. That means the union of A alpha is exactly X, and they are actually either equal or disjoint. So, they form a partition. So, that means A alpha either equal to A beta or A alpha intersection A beta must be empty for all alpha not equal to beta in capital lambda. So, such a collection we call it a partition of capital X. So, in general set theory there is a way actually to get partition. Actually having a partition is equivalent to such a way. So, let us see what is that. Okay. So, that is actually motivates us to define what is called equivalence relation. So, partition can be obtained from equivalence relation. Let us see how one can obtain. So, first of all, let us define what is an equivalence relation. So, again we fix this capital X, and then we want to define an equivalence relation on capital X. So, generally we write relation as tilde. So, let us fix that notation. So, a relation tilde, so a relation. So, a relation by definition it is a subset of X cross X. So, a relation, so by definition it is a subset of X cross X. So, is said to be an equivalence relation if it satisfies three properties. One is reflexive, second is symmetric, and third one is transitive. So, let us see what it is. So, the first one is called reflexive. So, that means X should be related to X for all X in capital X. And the second condition, it is called symmetric. So, if X is related to Y, then that should imply Y is related to X. So, that means X related to Y if and only if Y is related to X for all X comma Y in X. And the third relation is called transitive, which is very important relation. So, whenever X is related to Y and Y is related to Z, then that should imply X is related to Z, and this should be true for all X, Y, Z in capital X. So, basically an equivalence relation is defining a relation on capital X, and then that satisfies these three properties. And once we have this equivalence relation, then immediately one can define what is called equivalence class related to each element of capital X. So, for X in X, so what is equivalence class? Usually we denote it by bracket X. There are many notations that are used in the literature. Let us stick with this bracket X. So, this bracket X that is defined using this tilde is those Y in capital X such that Y is related to X. So, this is called equivalence class that is defined using this given element X. Basically, you have a relation on capital X, and then you fix an element and then collect all the elements that are related to X. So, that is your equivalence class X, and it is not that hard to prove. I will state it as a lemma and leave it as exercise. So, this is a very easy verification, and one can prove that if you take any two equivalence classes, call it class X and class Y, okay, for any x comma y in capital X. So, either the equivalence class X and equivalence class Y, they are equal, or otherwise they are disjoint. The equivalence class intersection equivalence class Y, they must be disjoint. Okay. So, in particularly what we can do, we can actually take all possible equivalence classes, form a set, okay, X in capital X, and then if you consider the distinct elements in this set, basically this is a power, this sits inside the power set of X, okay, because we collected equivalence classes. Equivalence classes are nothing but subsets of capital X, and in this collection, this set of all equivalence classes, they lie inside this power set of X, and then mostly they are denoted by this X modulo tilde. So, this is called the set of all equivalence classes, set of all equivalence classes, okay, of course related to that capital X and the relation tilde. So, now what one can prove, actually one can actually choose a parameterizing set for this X modulo tilde. So, what is it? We can call it capital lambda as the indexing set or the parameterizing set for this. So, it is any set that has natural bijective correspondence with this X modulo tilde. An indexing set of this equivalence classes is a set capital lambda that is actually has bijective correspondence with this X modulo tilde. So, then using this lemma, it is easy to see. So, here is a proportion that this X is nothing but union of this equivalence classes bracket X, where this equivalence classes runs over X modulo tilde. And in general, in most of the time in practice, what we do, we choose this capital lambda as a part of capital X only. Okay. So, in practice, we choose this capital lambda as a part of capital X, such that capital lambda intersection with any equivalence class will be just one singleton element. Usually that singleton element we call it as a representative of that equivalence class. So, this singleton called a representative of that equivalence class. Okay. So, in particularly this can be rewritten as X is disjoint union of this bracket X, where X comes from this capital lambda. Okay. So, that is why in most of the books they use this notation. Okay. So, this means we have chosen a set of representatives from each equivalence class and then represented them using this indexing set capital lambda, and X is nothing but disjoint union of this equivalence classes corresponding to the elements coming from capital lambda. So, that is very clear from this lemma, because the union of equivalence classes definitely will be exactly equal to X, but using this lemma it can be easily seen that given two equivalence classes, either they are equal or they are disjoint. In particularly they form a partition. So, what this proportion says, this collection, the equivalence classes where X is coming from lambda, so they form a partition of capital X, and it is not very hard to actually see. So, any partition actually comes from such an equivalence relation. So, what one can do, okay, one can start with a partition something like this, that is there in this definition, and then you can define an equivalence relation on capital X using this partition, let us say capital A alpha, alpha coming from lambda. So, you just declare the elements that actually comes from this one single A lambda, they are all related. Okay. And then you simply say that if elements comes from two distinct A alphas like A alpha and A beta, they are not related. Okay. So, such relation one can actually see that that will be equivalence relation on capital X, and then when you take the equivalence classes corresponding to such equivalence relation, that will be exactly this A alphas. Okay. So, I will leave it as exercise. So, here is the exercise. So, verify any partition comes from an equivalence relation. Okay. So, this is something we just verified. Okay. Given equivalence relation, how to get a partition, and we are saying that any partition indeed comes from equivalence relation. So, with this general remark, let us get back to our cosets. Okay. Let us fix a group G. So, G is a group. So, note that we haven't assumed anything about the cardinality of the group. Group can be infinite as well. Okay. And H is a subgroup of G. So, it is a subgroup of G. So, then we talked about left cosets of this H. Okay. Left cosets of H. And what we indeed proved in the last class that this left cosets, they form a partition of this capital G. Okay. So, these are called the set of left cosets of G. So, which we denoted by G modulo H. Okay. And then it is actually customary to denote the same G mod H for the indexing set of this set of all left cosets of G. So, what it means? So, we pick some representatives from each left coset of H in G, and then we collect them together as and then form an indexing set for this left cosets of G, H in G, and then that also again will be denoted by G mod H. Okay. As sets, one can identify the representatives and the cosets. Okay. There is no issues. Okay. So, what is the proportion that we proved? We proved that this set of all left cosets of H in G, they form a partition. Okay. This G mod H, X H. Okay. Now, I can call X in again capital lambda. So, if you want, you can actually see that this capital lambda is chosen subset of G that has bijective correspondence with G modo H. So, this is a bijective correspondence. So, we saw in our examples, okay, there is always a natural choice for this capital lambda. Okay. So, that is what we are talking about. So, if you are not comfortable with this, maybe I can actually just use the same notation. So, we often, like I said, we often write G mod H instead of capital lambda. Okay. So, we can say X H, where X H comes from G mod H. So, this form a partition of capital G. Okay. This is something we already proved. So, what is the proof? So, it is very clear that G is actually union of XH. Okay, let us again recall the proof because it is a very important fact. So, G is obviously union of XH X in G. Why? Because we already noticed that given any X in G, if we take XH, then X must be inside XH. Okay. So, that will imply G is subset of union of XH X in G. So, that is easy to see, and because XH they are all subset of G, because H is a subgroup, X is in G. So, XH must be a subset of G. So, this will be subset of G. So, that implies G is equal to union of XH X in G. Okay, this is clear, and we already seen that if I give you two coset, for example, call it XH and then YH, if they intersect non trivially, then that immediately implies that the cosets they are must be same. Okay. So, it means given two cosets either they are equal or they are disjunct. So, that is actually tells us that it satisfies the definition of partition, and so G can be written as union of all these distinct cosets, okay, where the distinct cosets will come from G modulo H. So, this is the partition that we get. So, this is indeed very nice partition of G in terms of cosets. So, why is the case? Because if I take any coset, this XH, we already noticed that it looks alike H. So, that means in more set theoretic language, so XH and H both are bijective correspondence. Okay. There is a bijective correspondence between XH and H. Okay. So, now we can state our important theorem, which is called Lagrange's theorem. So, what Lagrange's theorem actually tells us that if you restrict yourself to finite group, okay, so then you can conclude from the remark that G is a union of this set of all left cosets form a partition. From that you can immediately conclude that the number of elements in H must divide the number of elements in G. So, that is called Lagrange's theorem. Okay, let me state the theorem. So, Lagrange's theorem. So, what is Lagrange's theorem tells us? So, you assume G is a finite group. Okay. So, let G be a finite group. So, in particularly I can talk about number of elements in G, okay, or order of G. So, recall order of G is denoted by O of G, which actually counts the number of elements in G. Similarly, order of H is number of elements in capital H, and for any X in G, order of X denotes the order of that element, order of X in G. Okay. So, now given a group G and a subgroup H of G, so we can prove that the order of H must divide order of G. Okay. So, that is the first part of the Lagrange's theorem. The second part of the Lagrange's theorem, this ratio R of H divided by R of H, it exactly counts the number of left cosets, number of left cosets of H in G. Okay. And if you think about it, so we have a natural bijection from the left cosets and the right cosets. So, in particularly this also actually counts the number of right cosets of H in G. So, number of right cosets of H in G. Okay. So, this puts lots of restriction on the order of H. Okay. Once you know that given a group is finite group, for example, it has some very particular order, let us say 8. Okay. Then the subgroups of that group G which has order 8, that cannot have, for example, order 3, because the order of H must divide order of G. Okay. So, the possibility, okay, as an immediate corollary, you can see if the group has order 8, then the order of H, the possibilities must be 1, 2, 2 square or 2 cube. So, these are all the only possibilities that we have. Okay. So, this already gives lots of restriction for the subgroups. Okay, let us see how one can prove this. So, from our earlier proposition, it is clear that G can be written as disjoint union of the left cosets. So, in particularly, so you have G equal to disjoint union of X H, where X runs over this coset representatives, okay, which we denoted by G mod H. Okay. Now, note that, so this equation immediately implies the order of G, which is the number of elements inside the group. So, that is must be sum of order of X H, where X runs over again G mod H. Okay. Because we have taken this group, okay, let us call this is G, and then we have divided this into H, X H and so on. So, that means, so if you want to count the elements inside this entire G, then you have to count elements in H, Y H, X H and so on. So, that is what this equation indeed telling you. So, now order of G is summation order of X H this, but we have already one bijective correspondence between X H and H. So, that is given by, for example, you can define a map from H to X H, that the map goes to H to X H. Okay. So, this is a bijective correspondence between H and X H. So, that means the order of this H is same as order of X H for all X in G. Okay. So, this is true for all X in G. So, if we use this in this equation star, so then from star what we get? We get exactly the order of G equal to, so you just sum it over, okay, call for example this G mod H as some x1 H etc., some xk H. So, these are all the distinct left cosets. So, then it is clear that order of H is nothing but order of order of G is nothing but order of H summed over from I equal to 1 to k. So, then that is exactly equal to k times order of H. So, it is not only saying that the order of G is nothing but some multiple of order of H, that multiple is determined by the number of left cosets of this H in G. So, indeed we are getting the number of left cosets is exactly equal to order of G divided by order of H. So, this is all possible because we are able to do this counting because we are assuming our group is finite. So, everything, all the subsets are finite. So, we can count all of them, even the number of left cosets will be finite and so on. So, we are able to count everything. Okay. So, that actually proves the both statements in one go. The order of H must divide order of G, and as well as the ratio is nothing but the number of left cosets of H in G. And in literature, this ratio is often defined to be the index of H in G. Okay. This is called index of H in G. So, there are many notation to actually to denote this, and sometimes people use this mod G colon H to denote this index. Okay. So, we just stick with this R of G divided by R of H whenever, if there is no confusion. Okay. So, it is a very powerful theorem. Actually, one can use this theorem to get many interesting corollaries. For example, one can apply this theorem directly to the groups that comes from number theory, and then we can get many interesting results in number theory. So, let us see many corollaries of this. Okay. So, I will first start with one particular corollary, okay, which is immediate. So, suppose if your group has prime order, okay, let us start with the finite group G, and then let us say the order of this group is prime, okay, which we denoted by P. So, then what is the conclusion? Then G must be cyclic. And not only that, G must be isomorphic to Z modulo Pg. Okay, because we know that there exists only one group of order n up to isomorphism, one cyclic group of order n up to isomorphism. Okay, once you conclude that the group is cyclic of order p, then it must be isomorphic to Z modulo Pg. So, how one can prove this? So, let us start with some element which is non-identity element inside G, and this is possible because we assumed p is prime. So, p must be at least 2. Okay. So, in particularly you should have an element that is different from identity, and then look at this order of x. So, the order of x must be greater than 1 because it is not an identity element. Now, order of x must divide order of G. So, that is what Lagrange's theorem says. Why? Because order of x is nothing but order of the subgroup generated by x. Okay, that is something we have already seen. So, order of this an element x is nothing but order of the subgroup it generates. Okay, this is something we have already seen. So, in particularly order of x must divide order of G, but order of G is a prime number p, and order of x is actually greater than 1. So, that would force that order of x must be equal to prime p, because prime p has only 2 divisors, one and only one non-trivial divisor, that is p itself. So, this tells that the subgroup generated by this x must be exactly equal to G. So, that means G is cyclic and G is isomorphic to p modulo H. So, if you notice, we also proved on the way another corollary. So, for any x in G, we also proved that order of x divides order of G, because order of this x is nothing but order of the subgroup it generates. Okay. So, now let us see how one can apply in some number theory examples. Okay. For example, one can prove easily Fermat's little theorem. Okay, this is the corollary 3. So, Fermat's little theorem, it asserts about some congruence, okay, for any integer a in Z and fix p prime number. Okay. So, let p be a prime number and for any integer a in Z, we have a power p is congruent to a modulo p. Okay. Whenever for any prime p, and when you take any integer a, you raise it power p, a power p, then that must be congruent to a modulo p. It leaves remainder a when you divide by p. So, that is what Fermat's little theorem says. So, how one can prove this? So, one has to consider, recall. So, we have this group Z modulo p Z. So, this is an additive group. So, this also has this multiplication modulo p, and then we can look at all the invertible elements with respect to the multiplication. So, this is something we already considered. Okay. So, this is the multiplicative group with respect to modulo p. Okay. So, what are this? So, if you recall, so the cardinality of this, okay, the order of this must be exactly phi of p. Okay, so this is the Euler phi function. So phi of p, we already proved that it must be exactly p minus 1 for prime p. Okay. So the number of elements in this, so these are nothing but those these are parameterized by those positive integers, okay, between 1 and p which are relatively prime to p. So you know that there are exactly p minus 1 such elements. So now we will use this group to prove this. Okay. For example, if A is divided by P, so then there is nothing to prove because A is congruent to 0 modulo P. If A is congruent to 0 modulo P, then A power P is also congruent to 0 modulo P. So 0 congruent to 0, so there is no issue. What if P does not divide A? If P does not divide A, then it is clear that I can look at this A plus PZ. So this element inside this group Z modulo PZ, and then it must lie inside this multiplicity group, okay, because this will be invertible element inside this group. So now if you take this x, then what will be the order of x? So one can easily see that order of x at least should divide the order of the group, okay, but order of the group is p minus 1, okay. So that means this x power p minus 1 must be 1 or identity inside this group G, okay. So that is what we are getting. So this x power p minus 1 must be identity inside in this group, but what does it mean? What does it mean this being identity? So that means a power p minus 1 should be, so when you take the product, so that should be equal to the identity inside this group is 1 plus pz, okay. So a power p minus 1 should be congruent to 1 modulo p. So that is what it says, a power p minus 1 is congruent to 1 modulo p. So now by multiplying a on both sides, because a is invertible element, so it is non-zero element in this group. So by multiplying by a on both sides, we get a power p is congruent to a modulo p. Okay. So that means it does not matter whether p divides a or p does not divide a, we always get a power p is congruent to a modulo p. Okay. So we will continue with other corollaries and other consequences of Lagrange's theorem. Okay. I will stop now. We will continue in the next lecture. Thank you.